Yes, another thing we can do is calculate, do a luminance calculation. We can calculate the brightness of any color. Let's again say that we have a color which is represented by a vector. Like this. Okay, so I want to calculate the luminance of so one thing we could do is to use the vector length, which is kind of like the magnitude of the color. So and that is actually not exactly what luminance is, but it's a similar thing. Oops. It turns out that if you you can make a physical interpretation of the and measuring of the way the eye sees the different colors, and that kind of modeling gives us a formula like this. Maybe a little bigger. And this is actually like a multiplication, like a component-wise multiplication of a vector. So it's like taking the vector v and multiplying it by another color, which is kind of a luminance reference color, which has these values. It's kind of a greenish color, and then it's greenish because green is the brightest of the three base colors. Just going to put a little annotation here so we can see what's going on. Vector there, and then I'm going to use this symbol. Oh, it's not very clear. Maybe a little more space. Like this. So this is a component-wise multiplication. And this is the luminance reference color. And from that we can also see that luminance reference color. We can also see the luminance of various colors, and that is the luminance of red is about 20% luminance, 0.2, and the luminance of the pure green is about 0.7. And the luminance of blue is about 0.1. It's actually a little less than that, but just roughly like this. Just put some little dots in here so it's more clear. And green dot. And glue dot. And then finally we need some to write this correctly. This. We can also we can actually Photoshop has a very simple function to calculate the luminance of colors, and that's just turning the image into grayscale. So if I discard the color information, you can see here that the green one is becomes the brightest, and this is the middle, and the blue one becomes pretty dark. Okay. So in this calculation we saw a component-wise multiplication, and that's another operation we can do on colors. Yeah, we can sometimes call that with the interpretation of what that is sometimes like a filter. It's like applying a color filter to some colored light. So we can call I'm just going to write a simple equation here. What it is now, these are both colors. They're both represented as vectors. And we make this symbol just to spell out the components of it. And the way we do it is, as it says, component-wise multiplication. So it's like R times FR, G times FG, B times FB. That's what it means. Let's look at what could be an example of this. Like I said, filters is a typically modeled by component-wise multiplication. What is going on? There. So imagine like a piece of plastic or a piece of glass, which is transparent but yellow. The filter color is yellow, so we use an RGB value for that, like this. And then we can use different kinds of, we can shine different kinds of light through it. Maybe white light. Maybe red light. And maybe purple light. Again, I'm using a light gray to represent white so that we can actually see it. Excuse me. We have a beam of white light, and a beam of red light, and beam of purple light, and we shine those through a yellow filter. Draw a little filter, piece of yellow glass like this, and then we want to know what color comes out at the other side. And we do the calculations. Just gonna there, a little smaller. The calculations are just doing the color. So white, and we multiply that by yellow filter color. One times one, first two components multiplied together as one. 1 times 1 again, second component. 1 times 0 is 0, so the result is yellow light. There. Let's do the same for the red. This is the red input color, 100, and we multiply that again by the filter color. And we do the calculation, 1 times 1, first components multiplied together, that's still 1. 0 times 1, 0. 0 times 0, 0. So the red light just passes through. Illustrate that. Yellow filter doesn't change the red light. Let's see what happens with the purple. So purple RGB is 101, full red, full blue. And we multiply that by the color, the filter color, which is yellow again. And we do the calculations. 1 times 1, 1. 0 times 1, 0. 1 times 0, 0. So that actually also becomes red, since it filters out the blue from the purple. And this. There. Good. Now we're going to talk about alpha values. What is alpha values? So what we do here is we add a fourth component to a three-dimensional color vector V. So we now the color is 4. It's a four-dimensional number. So we add this new RGBA, the alpha value. The alpha value is used to indicate how the color interacts with other colors in some kind of combination. So we already seen that the color can interact with other colors, like with subtractive light or with additive light or scalar multiplication. Well, that's, yeah, but the alpha value lets us do that in different ways, so the color can interact with other colors in different ways. The most common use of that is transparency. So we want to use the alpha value to indicate how transparent the object that we are describing the color of is. Let's say we have a surface which is red, but it's semi-transparent. RGB are of course red, 100, and the alpha value is 0.5 to indicate that the surface is semi-transparent. A little vector arrow there. I'm just going to annotate that for you so you can remember it later. semi-transparent, transparent red. And to use something like this, this is what a semi-transparent red would look like if I drew it on top of this white. Of course, it depends on the background, but it would be like this. So I'm going to illustrate that as well. What happens in terms of physics, like that. We are going to drawing a little eye that's seeing the object, and we have here is the semi-transparent red object. It's a diamond, and behind it there are some other objects, so we draw like two different objects that are seen behind it. I'm just going to color in these there, and let's say that the top one is white. That's easy. We don't have to do anything. And then we have like a blue triangle. These beams of light that are then cast toward the eye. I'm going to use this, well, it's a bit too dark, isn't it? I'm going to use a bit brighter, just a little bit gray so we can see it. That's like a white beam of light coming from the white object, and of course there's a blue beam of light coming from this. And now we want to calculate what that looks like. What is the resulting color in these pixels? Yeah, so we'll just make the calculation here. For the white object, what happens is that this color is combined with this color, and we multiply. Oops. We multiply the color itself by the alpha, so 1 times 0.5, and then we take the background color, the white coming from that's already there, and multiply with 1 minus the alpha. That's also 0.5. 0 times 0.5, that's the no green component in the red. 0 times 0.5 plus 1 times 0.5. So up here, the pixels will have, the result of that one is 1, and here's 0.5, and here's 0.5. So the pixels will look like pink, like bright red, washed out red. And that's actually the same color as the object has, but that's because the background is completely white. The blue object, what will that look like through the red transparent glass? Well, we can calculate that. We take the blue, the source color of this is 0, and the red, and 0.0.5 plus 0 times 0.5, and finally blue. So the result of that is 0.5, 0, 0.5. Hold on. And let's draw those colors in. So remember that we just put in the values here, like this: 100%, 50%, 50%. So it's this pink color. It's actually the same color as the object itself. And that's because the background is white. And we take this lower color and we say 50%. 0%, 50%. It's like this. It's like a dark purple. So this is the principle of alpha values and what is called alpha blending, or transparency. The final topic is color storage. We're going to drop that. Okay.